Welcome everybody. Thanks for coming. If I were you, I'd be tempted to go outside. This is some of the most amazing weather I've seen in San Francisco in a long time. So this is our Indian summer. This is way better than summertime. How many people went to the show last night? Appreciation? All the more, thank you for coming. If I've been out that late, I'd be doing something else right now. Okay, so my name's Kyle. If you have any questions, you can email me, kyle@delphos.com. A lot of the information from this presentation is on my blog at kylehaley.com. So there's two parts to this presentation. The first part, I'm going to talk about experiences that we had at work trying to benchmark I/O subsystems. Ran into a lot of anomalies, and we'll summarize our findings. The second part, I want to talk about reporting. If I have an I/O subsystem, how can I create a report that's easy to read and can determine whether that I/O subsystem is sufficient or not for our needs? So we'll talk about visualizing I/O as well as creating reports. So, given the laws of gas dynamics, if you ask me to predict a tornado, it would be difficult. Similarly, with I/O, given all the rules of I/O, it's actually difficult to determine performance ahead of time. Under certain loads, we see emergent behaviors that we didn't think about beforehand. So some of the benchmarks I've had to deal with at work. We sell an appliance that runs as a VM under VMware, so we could actually run on bare metal. So one of the big questions at work was, what's the overhead for running on VMware? And this is where I started about 4 years ago. I thought we could do these tests in like maybe 3-4 days, a week maximum. 2 months later, we're still banging on the benchmarks. So we have our own file system, Dnfs file system. We want to compare that to raw. Are there any overheads from our file system? We use Dnfs, so there's concern, what's Dnfs versus fiber channel? And then when we go into customer sites and they give us some storage to use and map our file system on, we want to know what's the performance characteristics of that storage subsystem. So these are the kind of situations that I've been investigating. So what tools do I use? Anybody heard of MOTS? One, two. So MOTS stands for Mother of All Tuning Scripts. And it was written by Tenel Poder and Adrian Billington. I modified it. It's a great script. I modified it to add some more specific I/O stuff. I wrote a script called ormon.sh. These things are on GitHub, and I'll show you that. Ormon.sh is basically like IOStat, except from the Oracle database perspective. On Linux, I use something like strace. If I'm on Solaris, I use dtrace. Dnfs has dtrace in it, and we act like a NAS filer for the databases. So on Dnfs, I can use dtrace, and I wrote a script. If you're on Solaris, you can use this too, io.sh, and it gives lots of detailed information about I/O. So this is probably the situation most of you all are in. You have an Oracle database running on some hardware, and it's hooked up to some fiber channel. So the tools I would use on a database would be MOTS, and then on Linux or something, I'd use strace to find out what's going on. My life's a little bit more complicated. We have, in our architecture, a customer would have like multiple copies of the same database. So three different instances of Oracle on 3 different machines potentially, coming into our appliance, which acts as an Dnfs NAS. And behind the scenes, we're actually manipulating one single copy of the duplicate blocks that are shared across all those. So we allow instance cloning. But this adds another layer. So then I add io.sh to look at our layer and see what's happening on the latencies at our layer. So this is MOTS, and I modified it. The orange section in the middle is what I modified. You can get the modified version on GitHub, on the Kyle Haley. What I've added, so it's really cool. It's sort of like top activity in Enterprise Manager. I've got load on the system statistics, megabytes a second, read, write. On the bottom, I have my top SQL, and the sessions executing the SQL. I have my top weights. What I added in the middle is I wanted more information about I/O, since I'm going to be benchmarking I/O. So I have the major I/O weight events, then I have the average response time for the I/O weight events, and then I've broken it down into buckets. What is the occurrence, how many I/Os occur in that bucket, going from 1 millisecond up to 1 second. This is a little bit simpler. This is ormon.sh. It's basically like IOStat except for database. So every 5 seconds it'll output a line saying how many single block reads I had, what was the average latency, log file writes, multi-block reads, direct read. So this is nice. I can launch this up and get a view really quick on what's the performance latency and I/O on the database like. So perspective what I'm basically going through. So Oracle instance, most connected instance on the OS is different. If you use strace. If I'm going over NFS, this is pretty important if you're into this stuff. IOS.py gives information about NFS, IO. Then at the Delphix layer, I've got a lot of, on the Delphix client, I have a lot of layers to deal with: TCP, NFS, our file system, and then IO is the same. So this is the things that I'm looking at. As far as the tools, again, they're on GitHub. IOH is on GitHub as well. What is IOH? How many people on Solaris here? So few. So if you're on Solaris, you might be able to use the script. Basically, it's going to show the reads and the writes coming in and out. So it's the stack. I'm coming in, so I'm a NAS filer. So I'm coming in on NFS. What's my NFS response time? ZFS is the file system in this case, and then IO to the backend storage. Same thing for writes. And then I have megabytes a second, average response time, size of the IOs, and the IOPS. Okay, those are sort of the tools and situations that I've had to deal with. So along the road, we came up with a bunch of rule of thumbs. We ran into lots of pitfalls, and I'll summarize the lessons that we learned. So what are the rule of thumbs in IO? If I've got spinning disks, I know there's some basic rules of thumb. If I want to know what the average latency is, it's going to depend on rotational latency, how fast does that disk spin, and how long does it take me to get to the track that I want to get to. So the seek time for most disks are about 2 to 8 milliseconds. Rotational latency, the speed at which we spin, we can determine the rotational latency. So this is the basic rule of thumb. Long and short of it, from my perspective, is 6 milliseconds is a good physical read. Starts sort of sticking the ground. So these are spinning disks, because sometimes my seek time is going to be near where I want to read. Sometimes in rotational, I'll be where I want to be. So sometimes I'll be really fast, and sometimes I'll be slow. So we see distribution of latencies. And this is what I would expect. Most of the I/O around 6 milliseconds, some slower, some faster. And then as our disks spin faster and faster, as they spin faster, I expect latency to go down. I expect the number of I/O per seconds that I can support to go up. I'd expect throughput to go up, so sometimes we get surprised. In this case, the 50,000 RPM disk actually had lower throughput. And why is that? Small little bit of detail. The 15,000K disk had a smaller cache on it. So we're going to be talking about cache. There's caching at all different levels. When I buy a disk, it's got a little cache on it as well. The SAN's got cache on it. OS has cache on it. Oracle has this buffer cache. What's going to determine the number of I operations I can support on my backend storage is going to be the number of disks. Number of disks times the number of IOPS they can support. Important to keep that in mind, because as long as I've been involved in IT, there's been a push to have larger and larger and fewer spindles, which means less and less IOPS, which as far as database people go, that's usually a bad idea. So somebody might try to sell me this really fast disk, but it's IOPS. It's just one disk, so I can't support many IOPS. I can buy a bunch of dog, slow, cheap disks, but if I have a lot of them, I can support a lot of IOPS. So the basic rules of thumb. So this is what I expected when I started running these tests. I want to characterize the workload. What workload are we going to support? I'm going to simulate that workload, measure the backend storage, and then document the findings. I thought it'd be really easy. What we found was more like this. Characterize, simulate, measure, observe, and we get something wacky that was either really bad or just impossible. So then we have to formulate a hypothesis. Why did that happen? Recreate our test, rerun it again. Did the hypothesis match or not? And reiterate and iterate. Okay, this is a good one too. If you start this down this road and you don't have any experience, I mean, I'll admit I did this too. It's like, okay, let's just run DD. I'm gonna see how fast this disk is. And you see lots of threads on the internet about this. So I run a DD read, maybe normal, 50 megabytes a second. I run DD read again, I get like 4 gigs a second. I'm like, this is like, what the, that's impossible. Well, there's problems with DD. For one, by default, it's gonna read the cache. So first time I read off disk, and then second time it's going to count from the OS cache. That's a big pitfall. If you want to use DD, how are you going to simulate scattered reads? Sequential is fine, but how do you simulate scattered reads, which is the main workload on the database? And on the third point, I said it right. If I do a write, it's going to dump it all in memory. It doesn't dump it to disk, so my write's going to be blazingly fast. As I mentioned, the reads come from the file system cache over there. And if you want to simulate multiple readers and writers, it's going to be really difficult. Summary of the story is don't use DD. If you're going to be serious about this, use FIO. FIO is amazing. There's lots of IO benchmarking tools out there, but FIO has the most options that I found and the most active community. I must have gotten 12 emails from the community this week. Modifications of the code, people asking questions. I'll mention this again, but people, this is an Oracle crowd. People ask me, well, why don't you use Orion? For one, I do a lot of NFS testing. When I first started using Orion 4 years ago, it didn't support NFS testing. And second, the first time we used it, we got these blazingly fast I/O speeds. We asked you to do just imagine like a gigabyte of random reads across maybe 100 gigabytes of data, and we got back these like half of a millisecond read times. Like that's impossible. I was like, what is it doing? So we ended up using dtrace. We found out that out of this range, it was reading the same blocks over and over again. So we're getting 100 reads per block, basically. So from that point on, I was like, I didn't trust Orion. Plus, it didn't fit all my needs. So what anomalies do we, so we set up our tests, what anomalies do we run into? So we'll go through these 10 anomalies. The effects of caching, shared drives, shared connections. The next 2, 4 and 5 are NFS stuff. Consolidation of I/O, fragmentation of I/O. 6, we're seeing more and more. What's the effect of tiered storage? I think 7, first write penalty. 8, elided, which is actually interesting. What's the effect of compressed I/O? And then storage maintenance. I think this first point is probably the most interesting for this crowd. I think it's really cool. We'll see some neat stuff in the next few slides. What are the effects of caching? So the first question that comes up when I talk about this stuff is like, okay, I want to explain my goal is to avoid caching. And the question that comes up immediately after is, well, why do you want to avoid caching? I bought a I/O system and it's got caching on it. If the caching helps my speeds, then it's great. Well, when push comes to shove, you'll reach a point where you're not going to be able to use your cache. Whatever. The first time you read, you don't read from the cache. When the system gets really loaded, I'm not going to be reading from the cache. I want to know what the latency is when I'm pushed to the wall. So I want to find out what's the I/O latency if I'm going around. So what we see with caching, like the I/O, so what was wrong with the Orion benchmark where it didn't read distributed across the region, it read a few blocks over and over again? Why was that a problem? Because the first time I read it, it gets in the OS cache. The second time I read it, I don't read from disk, I read from the OS cache. What did I want to benchmark? I wanted to benchmark the I/O system, not the OS memory cache. So things like this, if I see I/O is faster than 1 millisecond, I know there's caching somewhere. A fast disk read off physical disk is 6 milliseconds. If my average is a millisecond, I'm hitting cache. Another thing that we see sometimes, we'll get a throughput that's higher than interconnect. So I mentioned DD. If I do a DD write, it'll just dump it to memory. And if I'm on 1 gig NIC, I can only support 100 megabytes a second. If my write is doing a gigabyte a second or something, that's not going through the interconnect. It's not going to the disk subsystem. So main causes. The OS has a file system cache. Storage rates have a cache. As we mentioned with that 15K disk that ran slower, it has a cache. So this is mainly a problem with reads. So what's the architecture? So at the top I have the SGA from Oracle, which has this bucket cache. And below that there's a file system cache. And then we connect to some storage, it's going to have its cache, and finally we hit disk. And those 2 blue circles, one is FIO, that's the benchmark I use, so it doesn't go through Oracle, because we can hit the OS system cache. Slob is a thing written by a guy named Kevin Fossen, so it's a cool little I/O benchmark tool. If you really want to test the system for Oracle performance, you want to use Slob. You want to go through the Oracle. Okay, this is where I think it gets interesting. So, this was a query run on 2 different databases. One was the production database, and one was the development database. We went and looked at the DD file sequential reads, the single block reads for this query, and got the average. So we can see the number times weighted is pretty similar between it's the same query on 2 different systems. The number is pretty much the same, but if we look at the last column, average last, the development system was 9 milliseconds and production was 5 milliseconds. So they came to us and like, your development system is broken. Why is your development system so slow? It's on the same storage as production, same type of storage. There's something wrong in the way you're supporting this database. Well, there's a problem here. And this is what I think is probably the most interesting we'll take away from this talk is if people don't pay attention to this. Averages are misleading. So if the average is around, in this case, what is that, 3 milliseconds? And all I'm seeing is the average. I don't know what's really going on. This is a representation of a histogram. So on the bottom we have buckets starting at 50 microseconds going up to 5 seconds. And the black, the measurement of the black is how many occurrences of I/O at that latency occurred in that bucket. So you see a bunch on the below 500 microseconds. So that's coming from cache. That's not coming from spinning metal. And then we have the disk speed more around something around 15 milliseconds. That's coming off disk. The average sounds 3 milliseconds sounds really good, but the disk actually is really bad. We're benefiting from cache. So let's go back to our query case. What's happening in our query? We took the query, ran through a 2046 trace, and with the trace, we get every single I/O request, and we get the latency of the request. So I put together a script called again on GitHub, Oracle Trace Parsing, and what it goes through is it divides all the I/Os into histogram buckets. So we have red as development, blue as prod. It might be hard to read this out away from the screen, but what I can see, even though I can't read the numbers, is on the prod, the blue line, the first bucket has a big number in it. The first bucket for dev is empty. So production is benefiting from some really fast caching, which has to be the OS level caching. So personally, for me, this is hard to read. But if we put it in graphics, I think it's a little bit more visible. So this is what it looks like in graphics. So development, the red one, is the one that the customer is concerned about, said it was slow. Blue is production, which was acceptably fast. And what I see is in blue, there's these really, the first two buckets have a lot of occurrences in it. So basically, we're benefiting from OS caching. That's the only thing that can go that fast. Then I see another spike around 500 microseconds. That's probably the SAN cache. And then we start coming out here in milliseconds. That's going to be reads off disk. I don't know for certain that all these latencies correspond to these layers, but I can be, for the 10 microsecond bucket, I can be sure that is not coming from SAN. But this is basically a rough approximation. Those first guys are coming from the file system, OS file system. Second, coming from the array caching, and then finally hitting disk. And what do we see here? I see that the production has a file system caching that development doesn't. It has a big spike at array caching. That's not so big on development. And then when I see the red in the development and spindle reads, the spindle reads are actually way faster, fairly significantly faster than production. So ironically, the development database physical I/O is better than it is on production, even though the averages was slower. Well, what do you do about it? Well, the caches aren't warmed up on development. That's the problem. It wasn't the I/O subsystem. So that script, Oracle Trace Parsing, if I have two systems, one's slow and one's fast, I want to find out why before saying it's I/O subsystem. So the script will show the top weights, average times. It'll show histogram latency by I/O size for the I/O events. It'll show what execution plan we're using. Sometimes it's a different execution plan. We want to make sure they're the same. And it'll actually list out I/O per second as that query executes. It's a cool little script. So caching solutions. If you do use DD for little tests, and I do occasionally use DD for little tests, I want to avoid caching. For writes, I can add this flag, O flag equals direct, and I'll go direct to this. For reads, I can add I flag equals direct. If you're on ZFS, there is no direct I/O. But in order to avoid the caching on the OS, we can set a flag. So set ZFS set primary cache metadata and the name of the file system. Now, if I want to avoid the RAID cache, I have to have a data set that's bigger than the RAID cache. So that was the first point, caching. The second one is shared drives. Now, if I'm going to benchmark an I/O subsystem, ideally, I want to be the only one on those drives because I don't know what somebody else is doing. I don't know how many times I've gone into a shop and they've been like, you are the only one on the set of drives. And we test it, and then the results from the test vary. Every time we run it, we get, sometimes it goes up, sometimes it goes down. The explanation is somebody else is doing something on those disks. Seems pretty straightforward, but causes a lot of problems. Similarly, an interconnect. So whether I'm using fiber channel or Ethernet or Dnfs, if something else is saturating that connection, then I'm going to be competing with it. It's also good to know what the connection is. What's the maximum speed? Because if my I/O tests have a throughput that's faster, that's bigger than the connect, then I know there's some problem. The test is not doing what I think it would be doing. And then we get into some weird stuff. This is just NFS. I don't know if this happens on fiber channel, but sometimes I/O requests get consolidated. And we've seen this basically with writes. So because I consolidate, the latency goes up, but it's an optimization feature, throughput goes up too. So without those sync or desync, sometimes you see multiple writes get get aggregated in a single write. There's other weird things in Dnfs. On Linux, sometimes you'll see, I'll be watching the redo, and it won't be a sync write. And everybody knows this redo writes are synced. They have to be guaranteed to disk. But what will happen is it'll write an unsynced write followed by a commit, and that commit's what's going to guarantee the write. So the other side of the point is fragmentation. And this happens a lot on Dnfs. So I'll do an IO request, and that IO request will get fragmented. Just this past week, we saw a really good one. On Oracle 2G on Linux, the database was in direct IO over Dnfs. Scattered reads, multi-block reads, were broken down into single block reads. And on 11, this doesn't happen. We haven't quite figured out why. But it was really interesting, because in this particular case we saw this past week, all the data was in the OS system, operating system cache. And our scattered reads are taking like 8 milliseconds. So if I'm coming from the OS cache, I should be doing like 10 microseconds or less. And we're like, well, what's going on? What was happening is they had their NFS connections really slow. It's like a millisecond latency. And for each of those, so that their scattered read was 8 requests. Each of those 8 requests went and checked the data file out on the NS file server for attributes. It didn't read the data, just got the attributes. But each of those requests was a millisecond. 8 requests, 8 milliseconds for what should have been like 10 microseconds. How many people use NFS here? There's definitely some things to watch out for. The Oracle documentation recommends that Oracle go check the attributes of the file on the NFS server. But if you do that, you have to go do a request for every single read, and that slows things down. And I recommend highly to take it off. Oracle's confusing. There's actually a MetaLink note that tells you to take it off, yet all the documentation says to leave it on. So, I/O fragmentation NFS. Again, here's another problem with Oracle. They recommend that the read-write size on the NFS mount is 32K. That means any I/O request greater than 32K is going to get fragmented on NFS. But NFS supports 1 meg read-write, and I recommend highly to use it. A couple of caveats though, if you're on Sun, there's a kernel parameter that limits it still, even if the mounts are 1 meg read-write, there's a kernel parameter that limits it to 32K. NFS read size, so you need to set that up. On AIX, the maximum is 64K, but you can get a patch from IBM that boosts it up to 512. So next is read ahead. So what we see in the case of read ahead is sometimes the underlying I/O storage will try to see what you're doing and sees that you're reading sequentially, so it's going to read ahead and read stuff before you even request it. So that means by the time that you request it, it's already there. So we get speeds that are too fast. On the other hand, if it miscalculates what you're doing, it thinks you should be reading ahead, but you're not really reading ahead, and it slows things down. So read ahead can cause problems. If we see unusually slow, it might be cause read ahead. If you keep running the test over and over again, and it gets faster, then that could be a cause caused by read ahead. Next thing is tier storage. What we see is tier storage, bad performance the first time you run it. As we keep running, it keeps getting faster because it moves our data faster and faster storage. So you might have something like EMC Vmax, where you have flash, and fast SAS, and commodity SATA. So an example, second bullet point example, the initial test we ran, 8K random read, was 20 milliseconds per random read. That's really bad in my opinion. As we kept running it, we went down to sub-millisecond because it would move our I/O, our files to faster and faster storage. Next one, first write penalty. So sometimes the first time you write, you have to allocate more than you actually want to write, and you get a penalty for it. And this happens on VMK and VMware. The idea in VMware is you want to zero out all your files because otherwise the first time you write to an area, it's going to be slower that first write. So watch out if you're using thin provisioning. You might want to not use thin provisioning. You want to see like fast write speeds. This one really got me for a while. It's a lighted read. So what is a lighted read? In some situations, if the files, so in my benchmarks, when I'm using FIO, I give it raw devices, but underneath that could be something else. So, for example, if I'm on a VM on VMware, what looks like a raw device in my Linux VM is not really a raw device. There's some storage behind it. And in the case of things like ZFS, if ZFS says, I've never written to that area that I'm requesting reads from, it's like, well, I don't need to read it. And it just gets zeros back. So I run these reads from one of these raw devices, and I get these whippingly fast times. And I was like, what the heck is going on here? Well, it wasn't reading it. It just gave me zeros. So the workaround of this situation is, again, pre-initialize the storage. Same thing with the write penalty, pre-initialize. We'll get rid of the write penalty. Pre-initialize, and we won't have elided reads. What did this look like in my histogram? When I ran what should have been all physical spindle reads, I got most of my reads done in around 500 microseconds. Next, compressed I/O. So this again can be impossibly fast read times. What if I initialize my data set with all zeros and I compress it? I can compress a lot of data down to nothing, almost nothing. When I read it, I don't have to do much physical reading, and all of a sudden it's super fast. So if I'm getting overly fast read times and I'm using zeros on the compressed file system, it's a problem. To get around that, we want to use random data. So in the scripts that I supply on GitHub, I initialize the data range with random data. And the final thing is storage rankings. Something to watch out for. If somebody's doing resilvering, or I use Dnfs, if somebody's doing a scrub, this kind of things can slow down. Things to watch out for. So in summary, a lot of the problems that we ran into, we would get around if we used real data. So like first write penalty, if there's real data, I wouldn't have that problem. Elided reads, if I use random or real data instead of zeros, I wouldn't have that problem. So we want a workload to be real workload with real data. In order to find out where the data is coming from, we want histograms to see if it's being cached at what layer. We want the data to be reproducible. If it's not reproducible, like if we're going faster and faster, that might be tier storage. If it's going up and down, it's probably somebody else is using the infrastructure, whether it's the interconnect or the backend storage. We want our test runs significantly long that we can get stable data. And we want to use application data instead of just zeros. So the workload, we'll get into this a little bit later, but we want a workload that actually simulates what we're going to test, not just something like running DD doesn't simulate what we're going to do in the database. So we want a mix of I/O, we want a mix of reads and writes. We want to know that we're doing I/O sizes that we typically use in the database. The rates, we want to make sure we have a flag set right, like OSync or async. We want to decide whether we want to use direct I/O or not, depending on what our database is doing. FIO is cool because I can configure all of this. As mentioned before, we want to use histograms, so we can see if we're getting caching layers or not. We want to verify the tests are reproducible, so you run these over and over again, don't go for your first results. Again, if things get faster, probably a caching effect, or tiered storage. Performance is variable, somebody's probably sharing the infrastructure with you. Running time, we want the running time to be long enough that the result is stable. One way to do this is to double the running time each time you run it until you hit a stable state. And then ensure the data sizes are representative. One thing I try, again, the goal is to avoid any caching, which means I want to avoid the sand caching, which means I want to use a data set that's significantly larger than the cache on the sand. So, summary, this is the first part. It's important for all of us to forecast the I/O performance. As we've seen, this can be quite tricky. Ideally, the things that we ran into can help you spot any anomalies in your tests. If you're lucky when the test results are impossible because you know something went wrong, sometimes you might be hitting stuff but getting useful results. But if you know these anomalies, you know what to look for. So the second part of this presentation is how do we create a representative benchmark and how do we visualize it? So when we're going to create a test, what are we going to look at for performance data? I want to look at the number of users, latency, megabytes per second, IOPS, and how are we going to represent it? Line charts, histograms, multiple charts, how do we do it? So it sort of seems right for a 3D graph, like I've had users versus megabytes per second versus IO size. And I'm sort of surprised how hard it is to get 3D graphs. Excel has 3D graphs, they're not 3D graphs. If you look on the bottom right axis, it goes 1, 8, 32, 128, 1024. They're all spaced out equivalently. They're basically rows, they're not actual 3D graphs. That's a 3D graph on top right. But I looked around, and R has a cool 3D graph package. It's actually easy to use. well, before I get to R, this is a plugin for Excel where somebody forced Excel to make a 3D graphic. Problem is, I can't read the thing going on here. I am completely confused. What this is trying to show is that the green users increase size Y is constant, red size is increasing user is constant. So this is R. Actually really easy. This is all the commands I ran here, and I gave it a data set, and it sliced out the three columns I wanted to. So I import the library, scatterplot 3D, sliced out my 3 columns, and then I plot them. Boom. You can't see it really well, probably on the slide, but with R we just add a few tweaks. We have drop pins. We can actually draw lines, so now I can see my different IO size tests easily. But the long and short of it is, and this is what I sort of had a suspicion of before I did it, I don't need 3D graphs. So this is just a 2D graph, and I actually find it easier to read than all the rest of it. So each different color has a different IO size, and we see an increasing number of users. But one problem, if I'm going to plot users versus latency, we've already talked about a number of times that average latency hides important information. So I can have a line chart with, this is users on the bottom, latency on the left. But we know there's important missing data, so how do we visualize it? Now for one single run, I can visualize it like this. This is one benchmark, one user load. I can see the histogram. But how would I visualize it if I want to see multiple user loads in the same graphic? So I try to do that in Excel. Each color is a different user load. You see on the right user load. I don't find this very readable, not much I can do with that personally. And then I stumbled upon this graph. I thought it was really cool. You might say, what the heck is that? When I saw this, what I thought was, immediately, is on the bottom I could have the users, on the left I could have the latency, and then I could superimpose the buckets per run. So I did that in R. So the black line is the average. In gray I see my distribution of I/O histogram. It's the log scale. On the left, I see the latency log scale. On the right, I see my buckets. And to make it a little bit more readable, I added colors. Blue would be caching, latencies in the caching range. Green would be nice response time, and then yellow, red would be slow response time. The other lines are 95th percentile, 99th percentile, 99.9, and then finally max I/O. So this is getting a lot. I don't know about you. I mean, this is a lot of data in one graph, but personally, I like that. I can get this and really see what's going on across the tests. Finally, I added one last thing, which is the background color. So it's basically, the background now is a bar chart per test. So the first says all the I/O came from cache, so that first bar is all blue. And the second test, some of it came from cache, some of it was at acceptable speed, and some of it was in the yellow zone are unacceptable, getting slow. And then finally, I added throughput because it's hard for me to have an intuitive relationship between latency and my throughput. Is it still going up? Or is it getting so slow it's going down? So on the bottom, I have my throughput. As I can see, it goes up to 16 users, and actually, the throughput actually goes down to 32 users. There's so much contention that the throughput's falling. So then my goal was I wanted to create a IO report card for Oracle. If somebody plugs in a SAN, hooks it up, and says, here, Kyle, here's some storage for your database. I want to be able to tell them, I accept the storage or I don't. So I wanted a benchmark. So the things that are required, I wanted to benchmark are the types of I/O I'm going to use, the size of I/O, number of concurrent users, and then the tool. So I've already picked the tool, FIO. I already mentioned why I don't want to use Orion. But what load am I going to put on it? So what does the database do? So 3 things the database does. We have user queries, so we do small random reads, or we do large sequential reads. 2, we have the log writer that's doing small sequential writes, or it could possibly be larger sequential writes, depending on the load. And finally, you have the database writer doing random writes, random single block writes. But I sort of grayed out the data writer because I don't really care about it as far as performance goes. Users aren't waiting for that. Users are going to be waiting for their reads, and log writers are doing commits. So how do I put this together into a set of tests that I'm going to run? So I want to test random reads, sequential reads large, and sequential writes small and large or mixed. What load do I want to use depends on what kind of database you're testing for, but I might want just a single user or maybe 8, 16, 32 concurrent users, depending on what load I want. And what size I/O am I going to do? Well, it depends on your database, but the typical block size is 8K, so I chose 8K for my tests. For For sequential reads, I chose the largest chunk, which would be 1 meg. And then writes, I chose small, like 1K, medium, 8K, and then large, 128K. So now I have a matrices of tests that I want to run. I just need to script this and put it together. And I'm going to use FIO to do it. How many people have used FIO? So a few people. I love it. It's not the most user-friendly tool. The way to run it is pretty easy. It's the bottom line, $FIO space config file. Running is pretty easy, but I have to have that config file. And that config file is going to contain the things I want. So file size, what size area on storage am I going to use? I'm going to give it file names, these are raw devices. How long do I run it? 120 seconds. What kind of test or retest? What's the block size, aka? How many concurrent users? In this case, just one. Now imagine I have to write this for that whole matrices of tests. It's a lot to do. What happens when you run this test? It puts out a nice user-friendly output. This is what it looks like. Difficult to read. I marked and read the things I think are interesting. So jobs is one processes or one concurrent access. Latency, microseconds. I see the average is 141 microseconds. At the bottom, I have my histogram broken out of latency. And the very bottom, I have my throughput. Aggregate, that's the number of kilobytes a second. I want that to morph. I want FIO to run all my tests, and I want the output to be friendlier than this. So I put together some scripts on GitHub. FIO.sh will run that matrices. FIO parse will take all those outputs and format it into something that's readable. And if you want to graph it, there's FIO.r that creates a graphing function in R, and FIOG.r which will actually run through your set of results and graphing. What does that look like? Well, let's skip this. This is all the flags in FIO.sh, the shell script, but we don't really need to go into that now. Here, you can actually run it without any flags, but I typically set a few flags. I want to tell it. I use raw devices. If you run it without any flags, it'll use a file and file system. So here I'm saying FIO.sh, run each test for 120 seconds. -T, do all the tests. -R, here's the raw devices I want to use. -Z, this is the size or the area on the raw device I want to use. And then finally, what's the total megabytes I want to use. And then it runs through this matrices of tests. So this is ready to use if you want to download it. When you run it, that automatically runs the parse script, which will go through all those outputs and parse it. And what we see is the type of tests. I see three types of tests: read, random read, and write. I see the number of concurrent users. I see the I/O request size. I see the megabytes a second, average response time, IOPS, and then we have our histogram. So this is a lot easier to read than that output per test from FIO. But I want to make it even simpler. I want to be able to give it to a manager. So we put it in a report card. So the report card has 4 parts: random reads for 16 users. This is what our typical situation is. Sequential reads for 1 user, how fast can I read? And then the bottom 2 would be for the log writer, how fast can we write sequentially? So if we zoom in on one of those 4 tests, this is what it looks like. So I have the latency, and there's the gray line with the green legend, that's the average latency. The gray one's the 95th percentile. I give it a grade so my manager can understand what I think of storage. Then I have a histogram so I can see if I'm hitting any caching. And it's color coded, so blue is cached, green would be fast, just read, and getting into the yellow, red would be unacceptable for me. And so on the left, it's regular scale, and right is log scale. So those colors get squunched down. That's why the distribution looks different. One's log scale, one's average on. And this is the final output. I also give a scaling grade. What would happen if I up the number of users to the next test? Does it scale nicely, or does it scale bad? So this would be hitting a fair number of disks. If I was hitting a caching effect, I could see it pretty easily on the histogram. And typically, I want to avoid that. This is really bad storage. What we're seeing is that latency, red line, gave it a grade of D. It's 95th percentile. So 95% of the IOs finish under 898 milliseconds, almost a second. This actually happens. This is fast storage. This is pure storage. Gave it A+. we can see the average and the 95th percentile are right next to each other, so there's not much noise. And it's fast. It's like half a millisecond. You can see again on the histogram, it's all clumped together. Not much wobble. So these scripts are on GitHub. FIO.sh runs the matrices of tests. FIO.parse.shell puts out that matrices of results. And if you want to graph it visually, you have FIO.r and FIO.g.r. And that's it. Any questions on this stuff? Dnfs results. The question I hear is have we tried using Dnfs? Yes, I've done. I have a blog post on Dnfs. My experience with Dnfs is just for regular load, it's pretty comparable. On Linux, the number of outstanding IOs maxes out at 128. So if I need more than 128 outstanding IOs, Dnfs is a great option. The cool thing is Dnfs takes care of a lot of stuff. If I have multiple NICs, it'll take care of aggregation, which otherwise would be tricky, and that's really cool. And then you get some cool performance benefits. Is there another question? Can I comment on Database Resource Manager and how this influences it? So the question is on the IO calibration tool. I haven't used the IO calibration tool. Any other questions? Oh. Well, that's our, maybe Jonathan want to take this. In my experience, like, what I'm thinking about is like system statistics, where we look at the average IO. Possibly something to investigate. I haven't looked into it. Might be reasonable to plug in these values. I certainly trust my results more than Ryan. Anything else? Okay, thank you all for coming. Feel free to ask some questions after.